Welcome to Planet Geo, the podcast where we talk about our amazing planet, how it works, and why it matters to you. Before we get going, Chris. Oh,
no, go ahead.
Chris Bolhuis. What was that, man? What did somebody knocking on your door?
I don't know what's happening right now. Actually, so.
There's a ghost in your basement coming to get you.
There's something's going on. I don't know.
The Bolhuis household. There's always something going on over the Bolhuis household, and it's always a little suspicious.
Oh, what do you mean it's suspicious? Why does it have to be that?
I don't know. You guys are just up to no good, and it's always a little bit, murky. It's always a little murky over there in the Bolhuis household.
I don't know about that. I
you and
really
your wife
appreciate that.
Yeah, you're doing stuff now. You got the dog, the puppy stuff. Always making noises in the background. It's great. It's a wild time over there.
Yeah, it is. It is. With Maple, we're growing her out with. She's got a Lions cut to her now. For Detroit Lions, but we're planning ahead
for
also
Detroit Lions. That's great.
Yeah. She looks like a lion. It's awesome. And then for President's Day, we're gonna dye her head or use the some sort of wash to make her head white. Like George Washington. Yeah.
Oh, nice. Excellent. This poor poodle puppy that you've taken under your roof is just having a real experience over there.
Yeah, she is.
I mean, she's very cute, though. Very cute.
She's a Bolhuis.
We got to meet her a while back. Very cute. Very cute. Chris, this is a fun one. So, let's do some intros quick. Okay. You are Chris Bolhuis. You're my former high school geology teacher, but more than that, slightly more than that. You're an award-winning, national award-winning high school earth science teacher. You taught geology, basically AP geology. I got college credit for that class. A whole bunch of other people have since then. You also teach a summer science field course, which is 3 weeks of field geology, going out in the western United States to Yellowstone, what we're going to talk about today. And you are now teaching an astronomy class as well. So you and I, we started this podcast, Planet Geo, a while back, 4 years ago now. We have tons of podcast episodes there. And what we're going to talk about today is Yellowstone National Park, the Geology of Yellowstone, which is near and dear to your heart.
That's right. But I should intro you, I guess, if I have to. So you're Dr. Jesse Reimink, and I don't like to refer to you as doctor, but I will in this case. But because you get that goes to your head. You're overeducated, and you're.
That's part of our contract, Chris. You have to refer to me as doctor once in a while.
That's right. So as you said, you were one of my students. You went on after that to go to a small college in Southwest Michigan, Hope College, and then you got your bachelor's in geology, and then you went to Canada. You went to the University of Alberta in Edmonton, Canada, to get your PhD. From there, you went on. You did your postdoc at the Carnegie Institute of Science. Now you are a professor at the Penn State University. So, and we've been doing our podcast for we're getting old. We're getting long in the tooth here, Jesse. We've been doing this for almost 5 years now.
Yeah, we're getting up there, man. We're getting up there. Actually, one of my PhD students just analyzed some zircons from Yellowstone, actually, from the volcanic eruptions there, and is kind of focusing on that. So it's fun to see the scientific arc, kind of come back full circle to the first time. Well, not the first time, but the time I learned geology about Yellowstone was with you when I was a high school student on this summer science trip touring around. So Yellowstone National Park, here we're going to share this screen here, and we've got a bunch of images here. All these images you can find on our mobile app as well, which is the CampGeo mobile app. This QR code will get you there if you scan that. We have tons of visual podcast series. This discussion, we're going to focus on the geology of Yellowstone, really a high-level view. You can learn more details. You can get into the weeds on our mobile app. We have a bunch of audio series with these images, and a sub-selection of these images we'll show you, and we kind of go through that in this thing. But here's what our app looks like. CampGeo mobile app, scan that QR code to get access to it on any mobile device. Chris, Yellowstone, though, let's get to Yellowstone. It's near and dear to your heart. And so, it's near and dear to me too, but you've been there much more. You're much more, I don't know if in love with Yellowstone is the right word, maybe. Is that right?
Yeah, I don't know.
You do love Yellowstone.
I think you'd be hard pressed to find something more geologically interesting, or maybe you'd be hard pressed to find a place that's more exciting to actually teach the science of geology. There's just so much going on here that it's my coolest place to take young, budding geoscience minds. I love it. I absolutely love
Yeah.
it.
I think so, Chris. Let me ask you a question on that. Contrast this with the Grand Canyon, because the Grand Canyon to me is a place where the first principles of geology, like the basic rules of geology, are right there, dead obvious. You can see cross-cutting relationships. You can just see more rocks in the Grand Canyon. And you can see the kind of first principles of our field. But Yellowstone is different. Yellowstone has that. I mean, the Grand Canyon's amazing, and it's an awe-inspiring view. But Yellowstone is kind of like a holy cow, our planet is an active, dynamic, earth-shattering thing. These processes that are active, is that a better hook for students? I kind of view like, okay, go to Yellowstone, get hooked on geology, and then when you're learning geology, go to the Grand Canyon, and then it's obvious for you. Those rules and those principles are really obvious. Is that a fair juxtaposition between these two very famous locations from a geological education perspective?
Yeah, I think so. It's also, Yellowstone has this immense diversity of geology that you can look at and dig get dirty with. The Grand Canyon is, you have a lot of relative dating principles, and there's certainly a lot to see. I love the Grand Canyon. I've been there many times with my family, and we've gotten intimate with the Grand Canyon, but Yellowstone is just, I don't know. Like you said, I think maybe you have to be a little bit further along to truly appreciate the Grand Canyon. Maybe, I don't know. I get excited to take young people to Yellowstone.
Yeah. Okay. I mean, it's great. I think it's an amazing place with this. Okay. This image here we're showing, this is a GIF we made that just shows the breadth of geological history that is available to you in Yellowstone National Park and the full history of this. And we're going to focus a lot on the end of this, but there's a long history here, 2.7 billion years. This starting here, ancient mountains were formed 2.7 billion years ago. They're weathered down flat. That's kind of the starting point. The oldest rocks you'll see in Yellowstone, there's not many. They are there. I love old rocks. A lot of my research, at least in the past, has been looking at these really old, really deformed metamorphosed, what we call basement gneisses, and understanding how ancient mountain building events occurred. That's kind of my research field, so I love this early stuff. But really, the story of Yellowstone's, more up high in this diagram, and we're going to work through this. We're working forward in time as we move up in this chart here.
Yeah, that's right. But this also is not to scale. We couldn't do that. Right?
Yeah, it'd be impossible to do it. Yeah. No, that's a really good point.
This is a timeline that's not to scale, but it hits the highlights of Yellowstone National Park. It hits the geology of this amazing place. So we'll slow down a little bit with each one of these things and just kind of dig in.
Yeah. So Chris, I love your construct here of a hot air balloon ride. So can you give us an overview of what the hot air balloon ride is like? Give us a visual.
I don't know. It's just something that I think about. I would love to see the geologic history of Earth play out from the perspective of a hot air balloon, really, really high up looking down. So you get this kind of like a press box view of the playing field in front of you, and you also get a remote control where you get to fast forward through immense geologic time and then slow down and hit all the highlights with the pause button, or just get to just play it in real time and then fast forward through all the kind of boring stuff that happens in between, maybe, or the stuff where there's not a lot going on. So that's kind of our approach with this is hot air balloon. We get to fast forward through things, and then we kind of slow down and get into the details on it. That's just, I don't know, maybe it's every geoscientist's dream.
It's such a cool visual. I love this, and Chris is going to have the remote. Chris is going to allow us to fast forward, slow down, stop at certain events, and look around. And I'm gonna be in the hot air balloon. I'll be in charge of the little engine that when we want to go up high and look out, and when we want to kind of sink down low and get closer and look at the glaciers and things like that. Because sometimes we're going to want to be right near the ground level, and sometimes we're going to be nowhere near this place because it's pretty active and pretty violent, as you can see in some of these things. So, Chris, this scale's not linear. Let's start out with this. The scale's not linear. 2.7 billion years ago, that's a long, long time ago. Earth is 4.568 billion years old. We're fast forwarding 2 billion years from that point, and we're hitting 2.7 billion years ago. This is a long, long time ago. However, there are rocks from this time period preserved in this region in Yellowstone National Park that tell us, we can look in the details. We're going to skim over this part, but the details of those rocks, the rock record tells us that this was kind of an ancient mountain building event, collisional mountain building event, where we produce these really big muscular mountains. Then those things were weathered down flat. And then we don't have much of a rock record for over 2 billion years. So we have to kind of skip ahead. We're missing time. We're missing story. We're missing part of the book because we don't have the rock record to tell us the story of the planet in this particular location. So that's the stuff we know about the oldest rocks, and then we kind of got to jump forward a little bit.
Now you're done talking.
I can
give me the mic back, and
I'm going to just run the engine. I'm going to run the hot air balloon. You tell me when I want to go up and down. I'll do that.
We didn't really talk about this in the intro. We should have. Your specialty, your research. You're a research scientist, and you're a geochronologist. You're a geochemist, and you specialize in super old stuff. That's your thing. So,
Chris, it's why I get along so well with you, is because I love the old stuff.
That's true. I walked into that.
You got to give me more credit. That's a good joke.
That was pretty good.
I haven't used that one before you either, and that's pretty good. I'm proud of that one. I thought that was good.
All right. Well, shall we? Let's fast forward to so those Precambrian super old rocks. We don't have a lot to say about them, so we're going to hit the button and we're going to go about 2 billion years again. We're going to skip ahead. Now, it's totally reasonable that a lot happened in this time period. We have no record of it. Right, a lot of geology must have happened because it's such an immense amount of time. But we are going to zip through it, and we're going to get to 515-ish million years ago.
Let me just say one real quick thing, Chris. We don't have a record of it in this Yellowstone National Park area. When we kind of look at, in summary, over all of what we know about the Western North America and all the rocks in this region, then we can piece together a story in this interval, and it gets pretty interesting, but it doesn't really relate to stuff you'll see in Yellowstone National Park, hence why we're skipping forward. So, geologists have thought about this problem, and we've got some opinions, but it's not relevant to Yellowstone National Park and the rocks that you'll see there. So anyway, sorry for interrupting that. Skip ahead to 500 million years ago. What do we got? What are we looking at in the hot air balloon?
Yeah, we're watching this calm, shallow sea kind of invade the area. In geology, we call that a transgression. It's just we have this rising sea in the area, but it never gets really deep, and the shorelines are shifting back and forth all the time. And if we could see into the water, we would see things like trilobites, which is, Jesse, if you want to skip to that next image, then this is one of the typical life forms that we would see in the shallow sea. The kind of, I don't know, Jesse, these things, I love trilobites. I'm a big fan. They were really, really prolific. They were all over the place, every ocean during this time period for a really kind of a long time, actually, had these things kind of just, filter feeding and doing what they do, right? They look like horseshoe crabs, kind of, right?
Yeah. They vote very, very horseshoe crabby. They're very if you take a geology class, you're gonna hear trilobites. You're gonna think about trilobites. If you're even just kind of casually interested in rocks, you've probably come across trilobite fossils. They're everywhere in the rock record. Loads of different species, loads of different types, loads of different sizes. They're very good for the paleontologist to kind of put timestamps in rocks and say, oh, this trilobite species is located in this rock, so therefore it must be a certain age range because that species only lived in a certain time period. But they're swarming this sea. And Chris, I'm gonna, if it's okay, I'll skip ahead to the next image here and show kind of a visual of what we're kind of dealing with, what we're talking about here when we're talking about this shallow interior seaway. This is kind of what we're referring to, and this is kind of what the landscape would look like. Mountains in the east, mountains in the west, but the continent is flooded. The flat part of the continent is pretty well flooded with an ocean that you said is never gets really deep because it's still on the continent, but it's kind of bobbing up and down. The ocean sea level rises and then drops and rises and drops, and over that time period it's depositing rocks. And
a lot of rocks. And
Heck of a lot.
This sea was, maybe thousands of feet thick. This was not miles. This was not like a deep ocean basin that we think of today, but it was definitely saltwater. But we were having rocks like sandstones and shales and even limestones that were being deposited. And these rocks just kind of followed where the shoreline was. As the shoreline shifted back and forth, the rock types that belonged to that shifted with them. So you'd get these like pretty immense vertical stacked rocks. As the sea would deposit these things, it would sink a little bit because of the immense weight of it, which would allow for more deposition. And it just went on for, a few 100 million years where this kind of...
Exactly. So if we're in our hot air balloon, we're going to be above Yellowstone, what is now Yellowstone National Park. We're going to be looking east and kind of looking out across this ancient sea all the way to kind of the Appalachians until we see land again. So, but this goes up and down, deposits loads of sediments. What's the climate looking like in this interval, Chris? Like what kind of life are we seeing there?
Well, first of all, we're seeing a lot of changing life. We're going from trilobites to, heading into the age of the dinosaurs. And so we would have things like ichthyosaurs and plesiosaurs patrolling these seas, which would, these are really, really cool things.
Let's stay in the hot air balloon, though. Let's stay up in our...
But that's a cool thing, right? If we would be able to just watch this change take place, because we can do this in fast time. So we'd be able to rapidly watch this life change. And this was a much warmer and much wetter climate at the time than what, Yellowstone is currently known for today. So it was, warm and wet and...
Yeah. And so this Western Interior Seaway, we're depositing rocks. That's really the main point here, is that this seaway, this ocean, is depositing rocks that we now see all over the Western United States. And there's a huge record of this. You can follow this from, the Grand Staircase all the way from, in the east. We can see it in drill cores, and it goes all the way up into the west, into the thrust belts and things like this, into the mountain ranges. We see these rocks exposed all throughout this area now, in what is now North America. So what makes the change from this ocean, shallow inland ocean, swamping the continent really, to what we see today? What's going on? What's the change here? It's a big one.
It is a big one. I think about this a lot in terms of geology. Geology often has patterns. When you have a shallow sea, what usually drains the sea is some sort of uplift event. It can be just a general drop in sea level. That can happen where everything just kind of stays flat and sea level falls. But in this area, what we saw is mountain building was taking place. So you're uplifting, you're thickening the crust, you're shoving it up, which causes the sea to go away. It just drains the sea. So we have this next event, which begins maybe, the early onset of this is maybe 150-ish million years ago. It's something that we call in geology the severe orogeny. And an orogeny is it's a garbage can term for a mountain building event. So, right.
It's a garbage can term. Yeah. I mean, it gets applied to everything. Orogeny, it's mountain building. We're building mountains. I think that was a good description, and as far as we need to go into that particular
I think so. It's probably, just let me continue though, the pattern thing, right? When you have mountains, then you have the forces of weathering and erosion that oppose the uplift of the mountain building event. And so when the mountain building is over, the other force takes over. So you get these patterns in geology all the time. And this is just one of the examples of that kind of pattern that we often see, where you have a sea and then it gets drained by an uplift of mountain building event. And it's called the severe. So
the severe. Yep. And then Chris, what we're going to do, the severe orogeny, this is, really, it's not a minor one. It's there. You'll see it in the rock record. It's what's called a thin-skinned one. So this is one where we didn't have lots of deep faulting. We had lots of shallow faulting, and things were kind of rumpled, not really rumpled up. You're kind of stacking.
Like stacked pizza boxes. If you take a stack of them and tip one end of it over, the boundary between those boxes, these kind of like shallow fault planes, that's more of what we had with the severe orogeny. That's kind of
the severe orogeny kind of came first and started out there in the west, and then over time, this thing evolved into a much more muscular mountain building event. And I'm going to skip to this image, Chris. And this image is still relevant. However, let's frame it this way, that this used to be consensus model for how the Rocky Mountains formed. And it's called the Laramide orogeny. And this particular model is called the flat slab model. We'll talk about it in a minute. But This is under revision, like currently under massive revision. There's a couple other competing models out there for how you form the Rocky Mountains without this flat slab model. And so we're going to show it because it's still, you'll see it in textbooks a lot. I mean, it was consensus view as of 10 years ago. But it does not do a good job of explaining some very, very key features that people have pointed out. So is that a fair way to frame it? This is under revision right now. It's active debate in the scientific community on what formed.
So the idea was that when the Sevier started, this early mountain building that drained the sea or began to drain the sea, this was a normal subduction zone. So this is kind of like these plates hit and it dives down at, let's say a 45-degree angle. That's a normal
Chris, in this
subduction zone.
It's the start. It's the first two frames in this image that we're showing here. It's like this image and then this one. And that's like a normal subduction zone diving down. And that plate would have kind of dove down into the deeper mantle. Normal subduction zone, thin skid tectonics. Something changed. The debate is what changed. And can I run with the traditional model or the old school model real quick, which is this flat slab subduction, Chris? And then we can kind of just touch on the debate a little bit.
Yeah, sure. Yeah, let's keep it tight. But yeah, we can do that. I think we should because this is what people most often see. This is what
you'll see a lot in signposts and national park, signs and textbooks and what other people talk about with the layer matte orogeny. The flat slab model just says that subducting slab, for some reason, shallowed out and became more buoyant. So it didn't want to sink down in the mantle. It became more buoyant. When that happens, there's good examples of this happening on Earth in the central Andes right now. There's a flat slab going on. So that's the analogy. Basically, that slab, that oceanic plate, slides underneath the continental plate, and it pushes the entire continental plate upwards. So we kind of see this in the later frames of the model. We start to see mountain building events occurring here when that flat slab is sliding underneath. It's wedging itself underneath of the continental plate and pushing it up. And that deformation, that uplift, goes way inboard. That orogenic event goes way in from the ocean and extends all the way into the North American continent.
Long ways away from the West Coast is now.
Long ways, right? Yeah. So that's the traditional view. Now there's other very compelling models called hit and run models where you can have sort of Japan or bigger type things that kind of slam into the edge of the continent and then get deflected and moved up to the north. And it's a really complicated story and complicated discussion, but this is not necessarily as widely accepted as it used to be. Let's put it that way.
So the takeaway is that a change took place regardless. You had this kind of like thin-skinned mountain building, the severe orogeny. Then the laramide, it completely changes. Now we're talking about mountains getting shoved up vertically and a lot. And so these are like really young, they're really muscular mountains, and that is, we call those the laramide mountains. So if we skip
Chris,
down, Jesse.
This would be, I think either way, however this happened, this would be fundamentally amazing to watch from our hot air balloon. And you'd probably have to hit fast forward, but we wouldn't skip ahead. We'd hit fast forward and watch this happen. But this is like over the course of a couple million years, an orogenic event started to happen in this deformation, this uplift, all of a sudden went inboard hundreds and hundreds of kilometers. So not only is there uplift happening right at the edge of the continent, uplift is happening way inboard where we see mountain belts today. The sort of residual elevation gain of the Rockies is still kind of fundamentally due to this laramide orogeny, the original uplift event. And so this would have just been unbelievably impressive to watch mountains raise up underneath of our hot air balloon beneath our feet. And, if we had this beautiful hot air balloon, we'd be able to see actually, why did that happen? We'd be able to see, was it Japan smashing in its hit and run model, or was it a flat slab? We'd be able to answer the question, no problem.
That's right. Yeah, but what we'd see in the Yellowstone area, we're hovering above Yellowstone, is we would see these mountains being shoved up. And today we see them, these remnants.
Okay, here we go.
So so you have this kind of like ring around Yellowstone National Park where the central part doesn't have these. We'll talk about that in a little bit. But you have the Madison Range, you have the Gallatins, you got the Beartooths to the north, you have the Absarokas to the east and kind of the northeast, and you have the Red Mountains on the south. But conspicuously to the southwest of Yellowstone, there's a gap. You don't have any of these mountains. And that plays in a very important part of the story with Yellowstone later on when the hotspot intrudes this and just kind of like erases that record that was there. So there's a lot of evidence that says that this whole area would have been volcanic and mountainous like we see with the Absaricas today or the Gallatins today. These are awesome mountains.
If we're hovering, I want to just, hit that point again, Chris, and emphasize that these mountains that we're highlighting 5 mountain ranges in this image around Yellowstone National Park. You noted in the Southwest, there are no mountain ranges down there. We'll get to that. There's no mountains in Yellowstone. We'll get to why that is. But this whole area would have been these big, muscular, your description is great, these muscular mountain ranges, deep thrusts that go down really deep into the lower to middle crust, and they exhume rocks from the lower to middle crust up onto the surface. Really deep faults that penetrate really far down. They penetrate in, Chris, not just through the sediments, that sedimentary layer on the top and the surface that's maybe a couple kilometers thick. They penetrate down way deep into the core of the continent and bring the core of the continent up to the surface now, which is amazing for us geologists because we get to see that, study that. That's where the old stuff is. That's where the record of continent building actually is. So that's this deep deformation that happens.
And if we were watching this from a hot air balloon, we would see these these are like modern day cascades, right? They are similar to our modern day cascade volcanoes. Mount Rainier, Mount St. Helens, things like this, Crater Lake, Mount Mazama. That's what they would be. They were bigger than the Cascades are, but they would behave like that, erupting every hundreds of years to thousands of years, spectacular blasts. These are what I call Yellowstone's other volcanoes.
Because, I like that.
Everybody thinks of Yellowstone as the super volcano, the air quotes of the super volcano that volcanologists hate that terminology, and we kind of need to move away from it. But
what we got to use, Chris, is super space volcano. It's a super duper
because all
volcano.
Volcanoes are super. That's right.
That's right. That's right. Yeah. Exactly.
But these cataclysmic hotspot eruptions, which these are not that, but these were, and Jesse, like when they erupted, we know that they were spectacular. We know how big they were. We know where these volcanic centers were because we have things like lahars, these mud flow deposits that came sweeping down the flanks of the volcanoes, and they were knocking over trees and whatever kind of foliage was growing in its way and transporting them down into the valleys. We're down in the valleys. It was a much warmer climate. We spoke to that a little earlier. The climate at this time, we're talking 50 million years ago-ish.
Yeah, okay, great. Chris, I was just wanted to say that. You're talking 40, 50 million years ago, and the Absaricas are where we have a lot of these volcanoes, these ancient volcanic centers that used to be there, these kind of stratovolcano type things. Sorry, continue.
No, but these, they would rip up these trees and transport them down in the valleys. And the trees that grew high up on the volcanoes, these were normal trees. These were firs and pines and spruces and so on. But down in the valleys, we had actually tropical trees. We had magnolias and palm trees and breadfruit trees, these things that grow in these like tropics and subtropic kind of exotic environments, but they were lower down the flanks of the volcano. So those kinds of fossils that are preserved today within these mud flow or lahar deposits, as we call them, that's super important stuff in terms of piecing together the geologic story of Yellowstone today.
Chris, this was one of my highlights of the geology of Yellowstone National Park. It's just such an amazing story that we can do this kind of ancient climate record sleuthing by using ancient volcanic deposits that knocked down trees and petrified the wood. So you have these petrified forests, and if they're all standing upright, it means they're a little bit further away from the volcano. If they're all knocked down flat, they were probably right on the flanks of the ancient volcano. You can kind of map this out and map out these volcanic centers. Totally cool story. We don't have time to get into these details in this video. If you go to the CampGeo app and look at that book, we have a whole chapter on this basically because it's just such an amazing story. Chris, if we're in our hot air balloon, we've moved away a little bit because we don't want to get hit by one of these stratovolcano eruptions because those are pretty big. If we turned to the west, let's fast forward a little bit and let's hit kind of 17, 18 million years ago.
That's
something
more than a little
dramatic.
bit.
Yeah. Okay, fair enough. Just skip ahead a few 10 million years or so, right? No big deal.
That's right.
We're going to look to the west. because to the west, something dramatic starts to happen. What do you think this would look like?
So we're talking about 500 miles to the west. So we'd have to be pretty high up in our balloon to see this, but we would see it because along the Oregon, Nevada, and Idaho boundaries where they all intersect, that kind of corner area there, 500 miles to the west of us, we would see spectacular, cataclysmic, biblical eruptions, right? Starting back furthest to the west, these biblical eruptions that would happen every, within million years, sometimes hundreds of thousands of years. To me, I think of it as a buzzsaw. Because the plate is moving over top of a stationary hotspot. It's like you got this, there's a hotspot, and the plate keeps moving over top of it, and it just keeps erupting through that. And so as time gets closer to present day, we would see the eruptions get closer to us, kind of like this buzzsaw effect of, oh my gosh, we need to get out of here with the hot air balloon.
No kidding. And Chris, I just want to kind of frame the size that we're dealing with here. We're going to come back to this with more numbers specifically, but we were talking about the Upsaricas and these volcanic eruptions knocking trees down. That's kind of a Mount St. Helens level eruption. That's kind of broadly what we're talking about. So yeah, we wouldn't want to be very close to these eruptions. We'd maybe want to see them on the horizon and we'd be okay. These things, 17 million years ago when the McDermott volcanic area was happening, we don't want to be within multiple states of this. These are eruptions that are cooling the planet. They're throwing so much ash and dust and gas into the atmosphere. These are huge. These are monumental, earth-changing eruptions. And so not only are we seeing these on the horizon, but we're like seeing them on the horizon. We're like, we need to get away. We need to go away for a little while. Then we can come back and check out the devastation and the damage. These are huge.
Yes.
And
they changed the game.
They changed the game. And Chris, you and I have this very vivid memory of you teaching me geology. I was a high school student. We were driving this yellow bus throughout western United States on this 3-week summer science camping trip. We had just been at Yellowstone National Park, and we were actually driving through the Snake River Plains. We were headed headed west, actually, from Yellowstone, southwest in the Snake River Plain there. And you were just kind of quizzing me on geology stuff. Or actually, I came up to the front of the bus to like ask you questions about geology. And so you were just kind of pestering me, like not giving me the answer, but kind of provoking me with different thoughts and questions. And you were asking me, you're like, all right, we're driving through this big valley, right? What do you see in front of you? Okay, nothing, just kind of flat. What do you see behind you? Nothing, pretty flat. What do you see to your right? Bunch of big mountains. What do you see to your left? Bunch of big mountains. And you're like, okay, what happened? And, high school me was like, oh, okay, well, erosion, maybe there's a river, maybe, an ancient lake or something like that. And you're like, no, that doesn't make sense because of these reasons, blah, blah. So what's going on? And it frustrated me because I never really got there. You had to give me the answer.
Well, no, I asked you different questions. Then I said, well, the mountains on the right, do they look similar at all to the mountains on the left? Let's look at their shape. Let's look at their structure. And then you started to get to it.
Eventually. Took a while. And then, and what got me there was you said, okay, where did we just come from? Yellowstone. Okay. What happened at Yellowstone? We were standing there on this hike looking down into this big flat area. What is that? Oh, a caldera. Okay, it's a caldera, huge caldera. Okay, now Jesse, we just came from there. We're driving across this flat area. What do you think happened? And that's what kind of ended up getting me there. That like, oh, it's a volcano, a center of volcano that has scarred across the land and just blown these mountains away. And that is a really, these two images here, this image here is showing the track of the former Yellowstone, what's called a hotspot, which we'll get to, but it's showing a whole bunch of different volcanic centers that have happened in the past 17 million years as this hotspot blew its way across the landscape, blowing away mountain ranges and creating this massive scar called the Snake River Plain here. It's just an unbelievably powerful event or powerful force, this thing that is Earth. I mean, this is amazing that this can happen. It's kind of science fiction if you think about it.
It is. Skip on down to the next image, and let's talk about this a minute.
Let me just highlight one little like currently irrelevant thing. This McDermott one here, this far western one, this is actually where there's a huge amount of lithium deposit and exploration going on in a prospective mine for lithium, as lithium becomes very important to society. In all of our battery technologies, we want more lithium, and so McDermott is one of these areas where there's a lot of lithium. So anyway, I'll skip to the next one here, Chris. All right, what do we got here? I love this image. What's going on?
I do too. This is, I'm happy. I'm proud of this. We helped create this GIF that we're looking at here, but we have this mantle plume that comes up and in places below the lithosphere. So it's quite deep. And it's
real quick,
quite
Chris,
massive.
Lithosphere is the tectonic plate. We don't need to get any deeper than that. It is the tectonic plate on the surface of the Earth. So sorry to interrupt. Continue.
No, that's fine. But then what happens is like magma kind of like finds an avenue up towards the surface of the Earth. Not onto the surface. It's really thick and sticky stuff, or at least it gets that way eventually. So it rises up and in places within the shallow part of the crust. And that's the magma chamber that feeds these eruptions that we look at in the previous image, leading us to the 3 cataclysmic eruptions of Yellowstone. But this just shows that the hotspot basically stays put and the plate moves over top of it. And so there comes a time when it gets disconnected from the hotspot and is no longer going to be able to be fed by fresh magma injections. And so it's where volcanoes go to die.
Yeah, that's right. That's exactly right. So this track here that we're showing, the hotspot is currently under Yellowstone National Park, whereas 17 million years ago, it used to be under the McDermott caldera. And what's been moving is not the hotspot moving, it's the continent moving over the top. That's the point here to show this image, is the continent has been sliding over top of the hotspot. So, Chris, can I move to the next image here and we could talk about the scale of these things?
Absolutely.
Okay.
Because we said to not, volcanologists don't like the phrase super volcanoes, but we do use the phrase super eruptions. And so Yellowstone has had 3 massive eruptions in the last 2.1 million years. So it was 2.1 million years ago, it was 1.3 million years ago, and 638-ish thousand years ago. So all of them were big, but this thing puts it into scale because it's comparing it to like Mount St. Helens in 1980, Mount Pinatubo in 1991, compares it to the first, the second, and the third Yellowstone eruptions. I mean, this is really hard to put your mind around. Like, how do we wrap our minds around the fact that the big eruption 2.1 million years ago, the first one that is where Yellowstone is now, it was 2,500 times more voluminous in terms of ash than Mount St. Helens was. 2,500 times.
2,500. That's 2,500 times. This is huge. Mount St. Helens, the scale of geology, I mean, we've been talking about billions of years, and now we're talking about the scale of these things. It's really, really hard to wrap your head around. And
but
that's
it's fun.
okay.
It's fun. That's
but it's
the thing.
Fun to try.
Yes. Yeah. Absolutely. That's one of the draws to me for geology is the sheer, the concept of deep time and the concept of like immense power. We live on an amazing planet, and we just we need to learn as much about it as we can. That's
beautiful.
We have to figure this out.
It's just mental gymnastics trying to understand our planet. It's just a really, really invigorating scientific discipline to try and think about this scale. And this is why it's unique among other scientific fields. Thinking about time on this level, think about the scale of these processes. It's just astonishing. 600 cubic miles, Chris. 600 cubic miles of ash 2.1 million years ago. That's the first eruption in the current Yellowstone hotspot location. So we would have moved our hot air balloon a long ways away from Yellowstone when this eruption was going on. And then we could bring it back in and look at the devastation that would occur over the entire region because of this.
A long time afterwards, yes. Well, let me quickly, let me run these down because you got 2.1 million, then you got 1.3. So that's like 800,000 years in between. This one was the baby.
Real quick. The red cube is the first one. The purple cube is the second one. And then the orange cube is the third eruption. So we're talking about the purple cube now, which is the baby, as you said. Yeah.
Exactly. It's the baby, because this was only 280 times more voluminous than Mount St. Helens was. And that's still
Only.
a massive eruption. I mean, it's hard to comprehend this, but in terms of a Yellowstone style, it's quite small. And then you have the 638,000 years ago, 1,000 times more voluminous than Mount St. Helens, which puts it in the category of a super eruption. So of the three big ones in the last 2.1 million years, we had two super eruptions out of this, which changed the game, right? They affect the world. You know, it's hard to underplay that. But I do want to say, Jesse, because it's something that grinds the scientists that study Mount St. Helens and geologists in general, is this notion that Yellowstone is due for an eruption. You know, because they look at this, you get 2.1, 1.3, 640,000 years ago. And somehow the math works out in some people's minds where, it erupts like every 650,000 years. And I don't understand that, because that's not the time frame that we're dealing with, but it's closer to 750 to 800,000 years between eruptions. But volcanoes don't behave that way anyway. And it's a little bit grinding. It's catchy. And so some of these articles catch the eye of the general public, and it's quite misleading, I think, and it just drives people nuts. Look,
I agree. Yeah. There's none of this, enough of this overdue for an eruption kind of nonsense.
It is. So, that's right. Yeah, that's right.
Volcanoes are not regular. We shouldn't expect them to be. You can go yell at Yellowstone and be like, "Hey, you're overdue. You're late, man. Come on."
Yep. And it's, can we talk a little bit about like these three episodes? They weren't really singular episodes either. The 2.1 million year event, this massive 2,500 times the scale of Mount St. Helens, this probably lasted decades or even tens of decades, where you'd have eruptions that it would go quiet for a little bit and then punctuated again. Like that's much more likely something that we would have seen, rather than just singular one-offs and then goes quiet for a long
right.
time.
And then Chris, as we've talked about before here, after the big giant eruption, we have a lot of oozing out of the chamber. We have a lot of things that are forming obsidian. This kind of, the volcanic vent has been cleared after a big throat clearing event. Now you are clear and you can ooze out stuff later. So we get all sorts of this type of stuff occurring after these big eruptions. But then every big eruption creates this big caldera and clears out the landscape and kind of resets the surface of this area again. And so it's actually really impressive that geologists can go back and map all these different lava flows in really detailed work to tell the difference between these three flows, date these three flows, or date the three events with multiple different flows. It gets really complicated really quickly with the boots on the ground when you're looking at the rocks themselves, because there's all of this kind of, it's not just one single event. There's a bunch of different little events interspersed in there with any one of these big eruptive episodes.
That's right. But now let's imagine the scale of these, and let's go back to where we talked about all the mountains, the Absaricas and the Gallatins and the Madison Range and the Red Mountains and so on, the Beartooths, right? Why are they missing in the central part of the park, and why are they missing in the southwestern part of the park? Well, whatever the Yellowstone eruptions didn't just obliterate, when the calderas formed, they then cannibalized whatever was left. It sunk down in and got destroyed it collapsed kilometers, right? These are not small collapse events. And then the net result is lava flows then come and bury everything that is left behind, and it just flattens everything out. It's much lower and much flatter. So like I don't know, Jesse, did that surprise you when I first took you to Yellowstone? How flat the interior part of Yellowstone is,
Yes, absolutely, for sure. And it's kind of shocking, and again, because coming from the east, you drive across a bunch of different mountain ranges coming from the east, from Michigan, where we're coming from. And so you drive through the mountains and you're driving through these valleys, and all of a sudden you're like, oh, wait, this is Yellowstone. It is relatively flat. And the reason it's relatively flat is, again, because you said magma chamber empties out, land above it collapses down in on itself. And so it's a really dynamic process. So, Chris, if we end there with the volcanic eruption 638,000 years ago, we're going to skip forward a little bit and talk about well, we're gonna hit fast forward, I think, right, from our hot air balloon. Is that right?
Yeah. Well,
And
yeah. Let's do that.
and so what are we gonna see? What's gonna happen? What's gonna come onto the landscape that is relevant for the geology of Yellowstone as we see it today?
Yeah, Jesse, let's fast forward from 638,000 years ago to like 174-ish thousand years ago. And you had another big eruption. I mean, if you look at a high perspective, our hot air balloon, or even on one of the mountaintops like Avalanche Peak and the Absarokas or so on, and you look out at Yellowstone Lake, to me, Yellowstone Lake always looks like a hand. It's got the palm of the hand, but it's a very gnarled hand, right? The fingers, there are only like 3 fingers that are very gnarled, almost like witch-like.
These ones coming down to the south here, right? Yeah, coming down.
And then you get the thumb sticking off there to the west, right?
To the west,
and
right?
So
yeah, it's big knobby thumb. It's like kind of it's too big. It's way bigger than it should be. It's a
thumb that got slammed into the car door, right?
Yeah, that's exactly right.
This is a very misshapen thumb, but it's a thumb nonetheless. And so the diameter of this thumb is about 10 miles across, and it was created by this a really big eruption. Roughly 10 times the size of a Mount St. Helens kind of eruption. So very small for a Yellowstone type, but it blew apart and created a caldera within a caldera, which I think is just like really cool to think about, and it's a very active area. It's got it's a geyser basin there. So lots of hot springs and, smaller geysers within that part of the park. But that West Thumb area was created by a spectacular eruption as well.
Yeah. So then Chris, we're gonna kind of fast forward a little bit, I think, and probably hit the skip button, and we're gonna get to, I don't know, kind of in the last 100,000 years. We're gonna kind of slow down. We're gonna keep the fast forward on, but we're gonna kind of slow down. What we're gonna see is we're gonna start to see glacial events come through this region. And we had continental scale glaciers on the landscape in North America. Where we're from in Michigan was glaciated terrain. There's a couple central lobes up there where there's main huge ice sheets up in Canada that were spreading ice down south, and they're melting out. In this region, they were not connected to that huge ice sheet. We had a Yellowstone area ice cap. And there's a really interesting reason for this, is that if we go back to this image here, the Snake River Plain, this kind of low area, funnels air up towards the high point here in Yellowstone, and so we dump a bunch of precipitation there, and that happens today. If we just cool the climate, you're going to get a lot more snow in Yellowstone, and you end up forming this kind of ice cap. So we get this kind of ice cap forming underneath of our hot air balloon, and if we look to the north, we'd be able to see these huge, what are called the Laurentide ice sheet, huge continental scale glaciers start to kind of come south, and then they retreat back, and they come forward, and retreat back, and come forward, this very periodic cycle over the last several 100,000 years. And underneath of our feet, we'd see this ice cap grow and shrink and grow and shrink and grow and shrink, etc. And so the sculpting of the landscape, there's a lot of sculpting of the landscape that happened due to this glacial event, both here and in the Tetons down to the south. If we just kind of turn and look south, we'll see Grand Teton National Park. We got another audiobook on that one. The geology there, which is spectacular, very glacially sculpted. So what features can we see underneath of us that are actively forming by the glaciers here?
Well, the glaciers were going to work. I mean, we have tons of erratic boulders that were dropped off, like in Lamar Valley. They're spectacular up in that direction of the park. That's the northeast part of the park. They were scouring out Yellowstone Lake. A lot of people think that Yellowstone Lake is the caldera. No, the caldera, the overlap of the 3 calderas, we should say, is so much larger than just Yellowstone Lake.
Yeah,
it's hard to imagine,
right.
though, because when you look at Yellowstone Lake, it's the biggest high elevation lake in the world. I mean, it's a massive lake, right? And so we would see just scouring out, going to work on this. It was going to work in the Yellowstone Grand Canyon. It was scouring that out and leaving massive boulders behind there as well. It was like, we're talking about a really thick ice sheet. It would be really cool to see, because we'd be able to, if we were in a hot air balloon, we'd be able to hover above this and listen to the creaking and the groaning of this moving, living, dynamic ice sheet. Very cool to see. But
Chris, just real quick on the note of the lake, although the lake, Yellowstone Lake, half of it's kind of in the caldera, and there's hydrothermal activity deep in the lake at the lake bottom. Half of it's not really in the caldera with a lot of hydrothermal activity, although some. But those three fingers that we talked about, those are ice sculpted, yes? Those three fingers, the lobes going south, were kind of dug by glaciers, much like, some of the Great Lakes in the region that we're from, and the Finger Lakes and things like that. So
absolutely. So when then the ice starts to melt and you have a ton of water, because you had a ton of ice, now you got a ton of water, and it fills the basins. And, Yellowstone Lake at this time then was much larger than it is now. A couple famous places.
And we have
Valley.
This outline, Chris, on this image.
That's
is
right.
Showing this dark lobe is showing the extent of the lake at the maximum. We're there's all this meltwater around. Exactly.
That's right. So you had the lake extended much further to the north into Hayden Valley, which is where people love to go and see the bison and see the bears and see wolves. Extended into Pelican Valley and people go there for the same reasons. And at the northern edge of this, the water was kind of impounded by these ice dams, and then periodically these ice dams would just give way. They would just break. And so the lake would drain then, and you'd have these like rushing, flooding waters heading north through what is now the Yellowstone River, and then just going to work on the Yellowstone Grand Canyon, or the Grand Canyon of the Yellowstone River, carving that out in a very short order. This was not geologic slow time. This was fast, cataclysmic kind of stuff. The rock there was soft, it was faulted, and it had just powerful torrents of water moving through it. So it carved it in literally like months and weeks rather than, millennia.
Yeah, that's right. And there's a lot of different parts to this canyon process, and the combination of glaciers and meltwater and these big floods cutting through this weak, wimpy rock. I mean, what we're talking about here are both erosional forces. You can kind of see this in the rocks when you go to the Grand Canyon of the Yellowstone. You can kind of see that the rock is a little bit wimpy, and the reason the rock's wimpy is it's been kind of blasted through by a lot of alteration activity. These are really highly altered rocks, and highly altered rocks can get weak really quick. So glaciers took advantage of this. The meltwater, these outburst floods took advantage of this and just carved their way through this beautiful gorge and created this beautiful waterfalls. I mean, many of these things, Chris, is just spectacular scenery here, and just an amazingly cool story as well.
That's right. And then, like, really to round this out, Jesse, is then what happens next? Well, one of the really, I think, cool aspects of this is that when these lakes, Hayden Valley would suddenly drain, you had these really fast pressure differentials that were created, right? You had the weight of all this water, but you don't forget, we got a hot spot down below us. So you have super hot groundwater, literally superheated groundwater, well above the normal boiling point, but it can achieve that because you have the weight of all the water on it. And all of a sudden, all the water's gone, right? The water drained very rapidly. And that created then just this perfect recipe for hydrothermal explosions. Essentially, this groundwater would flash and you'd have these just unbelievable explosions. And I think one of the best examples of this is Indian Pond on the northern shore, right near the Fishing Bridge Visitor Center there, just a little bit further out toward the east. That's a hydrothermal explosion. That's a big crater that's still visible today. And you look at that, you're like, oh my gosh, those are the kinds of things that are more likely to happen in Yellowstone in the modern era. Jesse, just happened this summer in the Biscuit Geyser Basin.
Yeah. Huge steam explosions.
Yeah, lots of really spectacular videos of this where people were just walking it without warning. It just exploded. And this has happened, time and again, actually.
And Chris, this brings up kind of the reason Yellowstone is spectacular is in large part this amazing geological history that we've told, but it has also a lot to do with the fact that we're sitting, as you said, on top of the hotspot. And the ground gets hot really, really quick. if you just dig down, the ground gets hot very, 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 very quick compared to everywhere else on the North American continent. And there's a lot of water in the system. And the combination of those two things creates all of the amazing kind of otherworldly features that you see in Yellowstone National Park. The hot springs, the geysers, the mud pots, the fumaroles. You just kind of go across the landscape and it smells like sulfur, and it's kind of, the landscape is just oozing gas and water vapor, and then explosions are happening. It's just kind of science fiction landscape. It's beautiful, it's amazing, and it's driven by shallow magma chambers beneath your feet that this water is interacting with. And Chris, this image here is kind of the last one we'll show today, and this is just showing that like the features you get are dependent in large part on how much water there is in the system and how much alteration of the rocks and how much silica has been kind of eaten away by the water system. So at up high where there's not a lot of water, you get fumaroles. Down lower where there's more water, you get mud pots. And then really down in the base, you get hot springs and geysers where you're close to the groundwater table, basically. And that groundwater is, as you said, superheated. And so this landscape's just spectacular because of these features.
And as you said too, I mean, there are so many other details that go into the making of whether, well, do you get fumaroles, do you get mud pots, do you get hot springs or geysers, or all of it, right? There's so much detail in this, and we get into those details in our audio visual podcast series, you know, where we dive into just that one thing. We have we got a whole chapter on that,
just on that, how the acidity of the water interacts with the rocks and creates all this potential for deposition or not, and then that controls whether you get a geyser or a hot spring. I mean, it's a very detailed story. There's a lot of super interesting stuff, and if you're gonna go to Yellowstone, you know, it really enhances, I can tell from going to Yellowstone when I didn't know geology and then going after I knew geology. Knowing geology enhances your ability to enjoy the park and just be amazed by these features and understand the processes that form these things. Because Yellowstone, Chris, it's an amazing place. It's a place that people all over the world know. It's a place people come to the United States exclusively to see Yellowstone. And that's a very, very cool feature, and that just speaks to the sort of power and the history of this region, and the geological history is amazing here.
And there are still places you can go, Jesse, where you can escape the masses and see unrivaled beauty, honestly.
Just get off the beaten path a little bit.
That's right.
Yeah,
that's right.
Yeah. It is still a wild
Don't ever
area.
leave the boardwalk. Don't ever leave the boardwalk.
Right.
But you're on the trails, and it's got a really good trail system, and you can absolutely, totally within your legal means, escape the masses and just go see the beauty for the park.
It's a spectacular place. A spectacular place to learn geology, appreciate geology. If you want to know more about the Geology of Yellowstone National Park, scan this QR code, click on the first link in the show notes here, and you can learn a lot more about that. And we get into the weeds in our visual podcast series there with some other great images that help convey this message. Chris, any closing thoughts about Yellowstone before we wrap it up?
Nah, we got it. I'll get emotional if I go any further. So I'm gonna stop.
All right.
We don't need emotional Chris on this. So
it's an amazingly interesting place. There's a lot more that we don't understand. Scientists are working on a lot of these interesting problems that we don't understand about this history. And so stay tuned. It's an amazing place.
Excellent. Cheers.